the program is recorded, and you can watch. They can watch the session later, and you too can watch the session later if there is anything that you have missed. It's going to be about 35 to 45 minutes presentation from Yusuf, maybe less than that. And afterwards, we'll open the floor for question and answers. Dr. Yusuf Sani is a staff engineer at Xperi, a company based in the Republic of Ireland. He graduated from Lancaster University with a PhD in computer science. Prior to that, he had MSc and BSc in the field of computing. Without further ado, I will give Malam Yusuf the floor to present his presentation. Malam Yusuf, go ahead, please.
Okay. Good day, everyone. Nice to have everyone on board. This lecture is going to be on computer vision, and I shall start with one or two words about myself, even though Dr. Musaf has covered basically everything. I currently a staff engineer at Xperi. Just to make a clarification, Xperi is a global company. It's not an Irish company. Of course, I am in their lab in Ireland, which is their biggest European lab. So prior to that, I was in Skytech, and I worked in academia once at Kano State University of Science and Technology. So this talk shall be on computer vision. It's my understanding prior to this talk that there is no dedicated course for Ahmad Bello University area on computer vision. So by design, I made it to be high level kind of a talk. So I'm not going to delve into deep nuances of the topics that I'm going to cover. But in case one wants to go deeper, we can do during the question and answer, or if time permits, else we can talk after. So let's start with some form of what even we are going to talk about. We know that virtually all elements in one way or the other have the ability to see. And this is something that we take for granted. It's something easy. 1 year old can recognize virtually anything you show him. So this is a kind of skill set that it's easy. But is that so with computers? Definitely not so. So what a computer vision is all about how do we teach computer to process visual information, analyze it, and make sense of it. And in the recent time, we have seen huge advances in computer vision. And so much so that there is a prediction that in the current setting, the market of computer vision is around $12 billion. And this trend is expected to keep on increasing. So it's a huge market that covers, that virtually permeates almost everything we do as human. Today, we find computer vision used in almost all sorts of engineering tasks, from agriculture to healthcare, to smart cars, to defense, virtually everything, from analyzing human movement and manufacturing, where people do some quality control and verification, to something that is dear to my heart, which is healthcare. We can use it for cancer detection and quite a number of things. In agriculture, then there is quite a number: crop yield monitoring and automatic weed detections, livestock monitoring, all sorts of things these days rely on computer vision. So let me start with a little introduction of what we are going to do. Traditionally, what happened is that there is what we call classical machine learning or classical computer vision, and there is what we call the most recent that relies on deep neural networks. So let's take a step backward and understand what are we actually talking about and what are we going to be talking about. So in classical computer vision, what happened is that we take an image or a video, any spatial representation of data that we want, and then we pass it into a series of steps. And we start with what is called feature engineering. By feature, we mean a piece of information which is relevant for solving a particular computational task. So these are important features. So the first thing we do is that we do what is called feature detection. That is identifying the point of interest. What are the points on the image? Let's say you want to do some face detection. You want to identify things like eye, like nose, like chin, like forehead. These are features of interest. And then after we detect the features, then we find a way of extracting those features. By extraction, we mean we try to frame the data set, kind of a dimensionality reduction, something, then into a kind of a row of data set that we fit into a select into machine learning, usually traditionally machine learning algorithm. Then in traditional sense, that is in a classical sense, is that we rely on statistical methods, which means is that we have to select the very best of the available selecting algorithm. Let's see, support vector, or we can use other form of machine learning that are suitable for a given data set. And then we get the result. This is the way it's been done. This is the way for long, but until recently, we have seen clear change in the pattern and the direction of the way computer vision is done. These days, things tend to be more centric on neural network. Well, what means is that what this one does is that it does away with the need completely of feature engineering. We don't need to do any detection. We don't need to do any extraction. All we need to do is just take the image, feed it into a series of neural network layers, and then get the output. So everything is done in a kind of a black box approach. The whole thing saves us time of understanding. In the classical methods, somebody somehow have to have a kind of domain knowledge to decide what features are important, what features are not important. This is a really complex task to achieve. But with a deep neural network, all you need to do is just take your image, feed it into the network, and just find it in this one. Even though in reality, we do away with, in reality, we have done away with the need to do some feature engineering and algorithm selection. We still have to make a decision on the form of the architecture of the neural network itself. Traditionally, we normally rely on convolutional neural networks and its variants. So this is a kind of neural network that takes a spatial representation and applies some non-linearity to it over a cascaded layers and then give you the output of what you want. Next, I'm going to cover a number of domains in computer vision. So one of the simplest things we do is we classify things. We want to know whether this is a dog or a cat, this is a house, or we do it always without knowing. But in computer, this is not so easy. Up until 2012, people have been using classical methods to do this one. We do feature engineering, we select models, algorithms that best fit into the requirement, and then we do some classification. But in 2012, things somehow changed where AlexNet was introduced into the competition called Large Scale Visual Recognition Challenge, where it becomes the first one. Since then, virtually almost at least most of the application we know of computer vision are in one way or the other neural network dependent. AlexNet is a deep neural convolutional network. It's a very shallow compared to what we currently have. It has 7 layers, 7 hidden layers, and no more than 60 million parameters. It takes an ImageNet, and it returns you the class of the image. Since then, we have seen more capable network like ResNet, like Inception Network, BGG, and quite a number. One cannot count how many numbers. Virtually every day there is a new neural network for classification. So the next task is, in classification, we have to understand the entire image and then we make decision on it. In some situation, we just don't care about the entire structure of the image. All we need is the outline of the image. Something like cancer detection, we just want to know there is a cancer or not, which depends on this one. Somebody crossing the road usually doesn't have to pay attention to the image completely to understand everything about it. What you do is you just want to get enough information to make decision on time. So this is where segmentation comes in. Segmentation, what we normally do is that we group a number of pixels into a class. Generally, we have two types of segmentation. There is what we call semantic segmentation, where we classify every and single image on the entire canvas of the image. And there is a instance segmentation where we partition the individual objects. Most recent networks that we use for this one, it's what I love most. It's called UNet, where we have a contracting series of layers. You start with a large filters and gradually reduce the size of filters, increasing the channel size of your images until you contract it to a point, and then you have another version of it which expand the layer. So it's like kind of an auto encoder where you have an encoding part and decoding part. The novel feature of this network is that there is a corresponding link between the expansive and the contracting part of it. So this passes the information throughout the network. It proves to be really useful for all sorts of things. It was initially proposed for medical imaging, but now we see it used in virtually all domains. So the next thing is we want to detect images. What do we mean by detection? In detection, what we do is that we try to detect the presence of image, and then we create a kind of bounding box around the image and the object. Detection, it's something that we usually do all the time. We use it for cameras in security, where we want to know whether there is a criminal or no criminal, there is cards, what, and in smart vehicles where they want to know whether people are crossing the road or not. We've seen it. Some of the networks that we use are CNN and Experian, and most recently YOLO, which seems to be a lot faster. In detection, we just want to detect the object without actually categorizing what it is. There is another domain that we're interested not only in detecting the object, we want to recognize it. See, in this picture, we have His Highness the Emir of Zazzau, and he finds himself in Kano. And then we decided to be sure whether the person that presents himself truly is the Emir of Zazzau, because we have to accord him respect that he deserves. In that case, we want to recognize actually who he is. And in addition to detecting him, we want to know truly he is who he said he is. There are a number of techniques that we use. While technically, in theory, we can use some of the methods that we have for detection, but that requires a huge amount of data set to do that, because probably being recently installed, we don't have too many images of the email of Zazzau. So what do we do? Well, let's say a signature in a bank. You want to know whether this signature belongs to actually the person that says, this is my signature. So you have only one copy of it. So usually we use what is called Siamese network. You have two networks which are trained to see the distance between two given images. So it's kind of a similarity distance computation that we do. So if we have two images, we compare the distance between them. If it's within a particular threshold, then we say, yeah, this is who he said he is, otherwise he is not. So these are the networks that we normally use. Another important application of computer vision is pose and movement detection. This is something that it's used every day from, and typically we use them for sports, in medical health, where movement is detected for infants to know whether they are doing well or they are not doing. One of the most popular network and its variant is what we call movement net. This is using, what it does is that, what we do is that we take an image, we create a key points on it, and then we generate heat map. Then we pass the image that we want to make prediction into a network. Then the first part of the network is kind of an impedance that takes the image and distill the important salient features of it. And then the second part of it is the architecture that has a prediction head, is kind of regression points that gives you the actual points on the map of this canvas. They tend to be really robust and fast. Another important application is counting, and this is something that I recently worked on. Just imagine that you have a port and you want to take an estimate of the asset that you have. One way to do is you send a human to do the count for all the objects. But we know that human can do all sorts of errors, either maliciously or otherwise. Recently, scientists, what we have been doing is that you take a satellite image and you pass it through a series of computational layer, and then the model will compute the density function of the number of cars, fridge, or any asset of interest. And then you take the summation of it, and that returns the count of object. It has huge application, from first detection into using satellite to crowd control in stadium to planning to all sort of things. And recently people have been using it in stores to take inventory of their products. But this is not where it stopped. All that I covered so far, it's under the domain of what we call supervised machine learning. In this case, we have assumed that we have a ground truth of what we want to make prediction in. That, let's say we have actual images of the card that we show to the network to train it with. But there are instances when we either don't have the target, it's not supervised, which means we don't have the images themselves, or we want to make a decision out of images. Because in this case, if I know it's a cat, that's the only thing I do. I'm not going to be able to make any decision based on that. At least the machine learning will not tell me if I see the cat, I should run. Or if I see a lion, I should stay. It won't do that. But there's another branch of machine learning, which is called deep reinforcement learning. In deep reinforcement learning, what happened is that you teach the system to train itself. What happened is that you have an environment, and the environment, what you want to take action within the environment. So you have a series of action states are reward. By action, we mean what are the space of action that I can take in the space. By if I take as action, the state of my environment is likely going to change. And as the result of the action I take, then I'm likely going to get a reward. Imagine you want to train a robot to walk. Then one thing you do is that you use deep reinforcement learning to teach the robot how to do. The robot will start by walking. When he falls, he get a negative reward. When he walks, he get a positive reward. After taking every step, we take account of the action and the previous state of our environment, and then we return a reward. This cycle continues forever. Recently, we have seen this into computer vision, where people at the Google and other companies were trying to find a way of training and machine learning to learn to play games. And this is not for the game of it. There is a huge application. I will come to one later after this one, where you teach a game to, you teach a machine learning model to learn to play a game just from the pixel of the game. It's a little beyond the presentation that I'm doing, but if anybody who needs further information, probably we can talk later. But what it does is that you have a series of frames of video of the game passes through the deep neural network, and million times. This happens in billions of times. And then the system always take an action. And then if it scores a point, it reward its increase. If it fails to score a point, then it reward decreases. The target is to maximize the maximum discounted reward at the end. And this system is really good, and it's at the age of research these days. For those who wants to go into research, this is a field that I advise we should take note of. The beauty of this method that they have used have been recently applied in a number of domains. Recently, while I was working with a company, we take the same approach where we try to train a model to predict the number of virtual machines that you can allocate to a given server at every moment. And it's virtually identical system. The only thing we change is the reward function and the set of the parameters and the action that you're going to take. That's all, and everything works fine, and it was really excellent. So I advise people to check this one. So now we say a lot of good things about deep neural network in terms of its utility within computer vision. But then the question is, after this, what next? One thing that we should understand is that deep neural network are not the very best of how do I put it? They're not very robust, if you like. Many researchers has shown that even a slight change in the composition of the distribution of the pixels can significantly pull the machine learning into taking action that it shouldn't have been taken. In this case, what we see is that we have a panda that we train a neural network to do that, and we take a noise and we just added it to the image, and all of a sudden the deep neural network completely collapses and started thinking that it's given. And this has been shown to be consistent. This has security implication. Imagine you have a security camera and somebody somehow intercept the traffic and just somehow corrupted the images. This can have a significant implication on quite a number of applications. So this is an ongoing research. People who are interested in, they can take this one. It's a new domain and it's fertile for research. And another domain that it's important when it comes to the issue of research is data and computation. We all know that deep neural network and computer, they are greedy in terms of the data requirement, and they can take huge amount of computation time. To train a ResNet on ImageNet can take days, and you need a huge number of computation. So then the question is, do we continue training a model this way? There are a number of ongoing research that try to solve this issue. One important thing is transfer learning, where you already, let's say you train a ResNet on ImageNet, and then you use it to predict something. See, you have a just recently discovered species of a cat that we have never seen. We may likely not have enough pictures of that car. So what do we do? One thing we can do is that we can train a ResNet on ImageNet, and then we initialize another ResNet with the weight of the network that we have. And then with few images, we can train the net for the cat that we have never seen. Another research direction is meta learning and few shot learning. In few shot learning, which is just another variant of meta learning, you train the model to learn how to. So we train the model to learn itself. It's kind of a learn to learn kind of algorithm. Let's say in this case, we have a cat. One easy thing we can do is that instead of teaching the model to know this is a cat, we teach the model to extract the embedding of a cat. So we pass the cat and a series of cat and no cat into the model, and at each point it extracts the embeddings of this one. So when we have a cat and this is not a cat, then the system will compute the distance between themselves, and if the distance is small, then it says it's a cat. If it's not a cat, if the distance is large, then it says it's not a cat. It's a huge area. It's a vibrant research community now. It's something that a master student can go and investigate further. And then the issue of deep learning at the edge. This is something that is dear to my heart because this is what I currently worked on. Usually deep neural network has a couple of challenges, not restricted to computer vision, which is that the model size tend to be large. Because imagine you want AlexNet, very small network, 7 layers, you have 6 million parameters. In UNet, you have close to 20,000 parameters. So it's a huge number of this one. And the model can be large. So traditionally what we do is that we take the trained model, deploy it on a cloud, and then build an application that, let's say you want to do an image detector, you train a model and put it on your server, and then the app on your mobile device or on your computer capture the image, send it to the server, which does the inference, and then return whether it is a cat or not a cat. In this case, it's clearly the issue that we are going to experience a network delay, and power consumption can be an issue because during the training, it can be really compute intensive, latency network, model size. All these are the problem associated with the current architecture. So people have been started thinking recently is that how do we deploy the model at the edge? How do we use it? If I have a mobile device, how do I do all the inference on the mobile device? Perhaps even train the model on it. There is a huge, huge fertile ground for research. One idea is that we can work on the model. Another one, we can work on the training. Another way, we can work on the devices. When I say we can work on the model, it means we can take a huge model, apply a technique like compression, model compression to it. So this model compression will take a huge model and then compress it into few number of bytes. Another things we can do is we can do what is called quantization. We take a model and then reduce the number of bits that represent each given point in it. So let's say we are using a floating point number with representation 32, then we can just quantize the value and approximate them with 8 bits, clearly cutting it by almost a quarter, getting the model to almost 25% of its size, doing nothing apart from quantization. There is what is called sparsification, which means is that you take a model and you create a more sparse version of the model. All this idea works on the modeling aspect of it. Another dimension is to take the training of the model. We can use what is called a federated machine learning approach. Instead of training the model on one given server, which consume a lot of energy, we can distribute the training on a number of devices. And then each device will do its own training and then send it to the edge server. And the edge server will do the aggregation of the weight instead of getting the data. This has the advantage of, first of all, it won't be sending the data to the edge server. It only sends the weights. So we save the cost for network transfer. We improve the privacy because we don't need to send anybody's data to the edge. And then, but the downside is that there's quite a number of challenges inherent with the distributed system here, and network delay and other things, synchronization. All these are points that we can further investigate. So this basically all I can deliver at the moment. So if we have question, then we can start, because I said initially that it's going to be deliberately high level. So thank you for listening.
Thank you very much, Mala Yusuf, for the wonderful presentation. Unfortunately, people from Zaria cannot join us until this point, but the good thing is we have recorded the video and we will make it available to them, and they can follow up with questions via email or via LinkedIn. But I'll turn to our guests who number 25 at the moment. If there is any question, please feel free to raise up your hand and I will unmute you to ask your question. Or if you prefer to type the questions in the chat, go ahead and do that, please. Okay, so I saw one hand. Okay, go ahead, Mustafa. I mean, like you. Okay, I think Zaria, one person from Zaria is here. Yes, Dr. Mustafa, please go ahead.
All right, Dr. Mustafa, Dr. Yusuf. I hope you are all doing well, and thank you for the presentation, Dr. Yusuf. I'm sorry I couldn't join you as early as possible. I had to be in the Senate meeting. Again, Dr. Musab, I think there are a number of us from Zaria. Probably it's because I can see our students there. So they are there. If they have any questions, they can do on the general presentation. Anyway, I'm happy with the presentation on image processing and computer vision, especially the fact that Dr. Yusuf is bringing so many things together, where he brings the concept of image, video processing, the concept of machine learning, the concept of deep learning, and again, even the concept of game theory. So thank you, Dr. Yusuf, once again for this. Our students that are with us here, please, I urge you to take the best opportunity that you have now. If you have any question, if you have any doubt, any concern, or you have some problems that actually are in the domain of these areas that have been discussed, to ask questions and clarifications from somebody who is coming from the classroom or laboratory research. Okay, thank you very much.
Thank you, Dr. Mustafa.
Thank you, Doctor.
Yeah. So any question from Zaria or from any of the participants?
Oh, I have one.
Okay, go ahead, please.
Yeah, I'm Mukhtar. Thank
Yes,
you very
Mukhtar.
much for the presentation. I think mine is not, it's more of the question, not precisely a question, but let me first and foremost appreciate the presentation. Thank you very much, Doctor, for the presentation, and also Dr. Musa. Mine is just like, as I said, it's just a request. Doctor said he made it, he deliberately wanted to make it an advanced presentation. I don't know if there's any way people like us that are just beginning the course, like can have some introductory, aspect of the concept. Yeah, I don't know whether it could be very deeply or there's any way the doctor or Dr. Musa can refer us to. Thank you very much. I remember the from Sokoto.
Okay. Okay, so for somebody who is willing just to go into computer vision or anything these days, in theory, there is a large number of online classes that you can avail yourself with. You consider it's good point to start. You can go, there is a number of machine learning and computer vision stuff. But for somebody who wants to go truly to computer vision, what I will advise is that the first one, work on your mathematical skill. Statistics is very important. Linear algebra is very important. Computation somehow depends on this too. So first of all, polish your linear algebra and statistics. The second thing is that programming cannot be overemphasized, particularly Python. Most of the libraries that we use these days are written in Python, but of course we can use other languages, but that's the language that most computer vision people and generally machine learning likes. So Python, it's very important. One needs to understand Python. Then the second thing I will advise people is that don't just jump into deep neural network just because it's something that everyone is talking about, is everyone use it. The classical methods can be really effective and it will give you a clear understanding of the reality of things. Because with most deep neural network, I skipped that deliberately because it's something that been going, there is a huge number of arguments about it. That is, it's a black box kind of approach. We just take an image or any data set, pass it into some kind of magical box, and then we get an output. And we don't necessarily know what is going on in the box. So there is discussion of interpretability. What we use, is it interpretable? Can we explain it? The issue of explainability, all these things makes the matter worse. Imagine that you are a patient, you go to a doctor, and then a doctor tells you that, hey, you guys, you have this particular disease, you have a cancer or anything. One will naturally wants to know, how does the doctor make such a conclusion? But with deep neural network, we are likely not going to get the kind of answer we want because we may not necessarily understand how it works. Of course, there is a new field of machine learning. Explainability is a vibrant area and it's something that people who are interested can go in and do further research and expand the frontier. But then let's come back to the beginning, which is mathematics, linear algebra, statistics, programming. Start with classical methods, then you can move to deep neural network. So I think this sequence can help somebody who wants to learn. You can go for Coursera. They have a number of excellent courses. There is another avenue called EDX. There is a large number of, and YouTube, it's an excellent resource too. And after, we are going to include some number of links that we think will be helpful for people who wants to start.
Thank you very much, Mali Yusuf. I can see Abdul Ashara Tate raising his hand. Go ahead, Abdul, and ask your question.
No video. Okay, assalamu alaikum. Dr. Yusuf and Madam Musab, thank you for organizing this, well, I call it a conference, and for a wonderful presentation from Dr. Yusuf. May Allah subhanahu wa ta'ala reward you abundantly and increase in wisdom and understanding. Okay, thank you. What I picked from your presentation, I think this is the first time I'm sharing the YOLO object detection algorithm, a neural network. I'm sure it has to do with a convolution and neural system. So, Bala Yusuf, if you could please just give a brief overview of about a YOLO object detection algorithm. Thank you.
Thank you, Abdul.
Okay, thank you. The reality is this one. If we go into detail of explaining each and every single algorithm, we're going to spend the whole hour of it, but I'm going to try to explain the essence of it. And then if you need further information, I can send you the link, because this is something that requires a number of equations, a number of more modeling, the talk of the architecture. So it's going to consume the entire time. So I'm really sorry if I'm brief and high level. This is the deliberate, but we can talk after the presentation. So in YOLO, what happens is that you want to detect an object. There is a kind of, prior to YOLO, what people normally do is that you take an object, you then create a region from the object, which is called the region of interest. And then each region, you just pass it through the neural network, and then the neural network will make this decision on the region. So it turns out that you have to know which region to take, because let's say you want to detect a cat, and the cat is very small compared to the large size of the image. So you will end up sending spaces that contains no relevant information for the task, and wasting computation and other things. So what researchers later realized is that instead of the region-based, which you can use one short kind of design, that is, you create a bounding boxes, and within the whole image, n number of bounding boxes, that n can be 19 and multiple of it. So each region, you pass it into the network, and then you make decision based on that bounding boxes. And then the neural network will make decision that, first of all, is there an object in that box? If there is an object, what is the bounding box? What is the bounding dimension of the box? So it returns the object, the definition of the bounding box, and then the system continuously train itself. Usually you train it in what is called mean over intersection methods, which means is that it's going to take the image you give it and the expected output it produces, and then it can compute the MIOU of it, and then continuously applied the optimization over that until the model reach a point where you can make a decent prediction. I hope in this brief I have covered something that is beneficial to you. But after we can talk.
Yeah. Yes, thank you, sir.
So there's some questions in the chat. One says, "Thank you for the presentation. Please, can we get the presentation slide?" The answer is yes. We usually upload the recording on YouTube, and we put links to some of the slides and the materials that are used in the presentation. So if you search recent advances in computing on YouTube, you should see our page. Subscribe. I'll just type it, recent advances in computing. If you search this on YouTube, you will get our page, our channel where we upload these videos. And below each video, we will provide the slides and anything relevant to the presentation. Another question in the chat says, do you see any good, from Aminu Abubakar Ali, do you see any good chance that machine learning program can detect feature without being trained, in bracket unsupervised?
Oh, yeah, definitely. We have used okay. Unsupervised doesn't mean we don't have a feature, so we have to sort this one out. It means that we don't have a target images or target output. Let's say you have a level image. You have an image that contains all sort of things in it, and you have not sat down for some reason to label it. You didn't tell the image there is a cat, there is a dog, there is a house. You didn't do that. But you still want to make decision on it. Of course, there is a way you can do that. There is a non-supervised machine learning approach. The easiest thing to do, you use clustering algorithm. Clustering algorithm, what it does is just take the image and then try to find group the pixel that are alike into one point, and then traditionally we use that for segmentation. So they cluster the image, the image that are likely to be similar to one another in one box, and those that are different in another box. So you can create a number of clusters, and this will create kind of segmentation in your image. This is one way to do that. In a more recent way, you can use what is called a variant of autoencoders. So you can take an image, let's say you want to segment an image. You can typically build an autoencoder, which means is that you have a neural network that starts with the large filters and gradually reduces its sizes until when you have a smaller computational layers at the middle. And then you start expanding the layer, upscaling it gradually, upscaling it. And then until when you have the input and the output are the same, then you can train the model to try to predict the input image that you already fed into the model. So this has been used for a number of fields like anomaly detection. Let's say you want to know if there is an anomaly in something or there is no anomaly in something. Like in an image, there is all the image contains, you suspect that a criminal has somehow used some image to infiltrate into your system. It's likely that the images that the criminal has done somehow altered the distribution of the image. So they tend to be anomaly compared to the rest. So what we do is that we use autoencoders, train the model to know what is the right image, and then we fed in the image that we suspect. And they are likely going to deviate significantly, then we know they have contained something. If they don't, then we know that they fit into the profile that we desire. So yes, the answer is yes. There is a way you can use non-label image to do machine learning, and it's a fertile ground for research.
Thank you very much, Malam Yusuf. Another question from the comment says, is it that computer vision technology in vehicles, this is from Abdurrashid Alami, is it that computer vision technology in vehicles is more suitable with the autonomous vehicles, or can also be used to manage the traffic with normal vehicles in traffic management? I think what he wants to say is the computer vision used in autonomous vehicles can you also use the same technology for vehicle traffic management?
Okay, and when we say autonomous vehicle, we are talking about a huge thing, because if we take a little step backward, at the moment we don't have one, we don't know how to train one model to do everything like our brain does, because our brain has different parts trained to do different things. Up till now, we have not reached the point that we do that. So what we normally do when we have a complex task, we have disparate pieces of neural networks, each one trained to do a particular task. So when you have an autonomous vehicle, what you are saying in essence is that you have a collection of machine learning models that collectively act to enhance the way the car drives. This can be it drive itself, or it can assist human to drive itself. So those models that we use to train a car or to walk, of course, we can modify them to use them for other purposes. Nothing stops us from using the image we use, the model we use to detect if somebody is crossing the street in a car, nothing stops us from using it on a traffic light to know when somebody is crossing or not. So the application is independent on the way you train things. Well, I'm not totally correct, but the way we train model is essentially task specific, if you like. So if the task find itself in a number of domains, so be it. If it's not, then we have to retrain the model for a different task.
Okay, thank you very much, Malam. I think there's someone here. I keep muting people, but then all of a sudden you hear someone popping up with some background noise. Any other question? Although we started late, we have exhausted our hour, but we can take one more question if there is. Otherwise, I will call on if the HOD of ABU Zaria is here to give a few words before we close the session. Please, can you all check and mute yourself? I couldn't find the person whose background noise is really.
Is somebody, Mohammed Lawal, asking a question, Doctor?
Okay. Mohammed Lawal, yeah. Okay, there's Infinix S5 Pro also.
Okay.
There is no name. Okay, Mohammed Lawal on the chat. Okay, thank you for no. So there's, I don't know, do you have a question? Infinix X5 Pro, S5 Pro. You have unmuted yourself. Okay, I think Muhammad Lawal. Who is Muhammad Lawal? Okay. Any question? Okay. So I think we need to draw the session to a close because we have exhausted our hour. Unfortunately, we didn't start in time. But all the same, thank you very much, Malam Yusuf, for the wonderful presentation. Just to recap, we are doing these sessions purposely to give our postgraduate students in different Nigerian universities the opportunity to come in contact with people who are doing real research across the globe. And this will help them in defining their research career and in understanding where the research is currently going. We have done this with a number of universities, and we are happy to come to your university and discuss topics of your interest. Just get in touch with us. As for me, I am always available on Facebook. You can send me a message. You can also contact me via LinkedIn, and we will arrange to have a session presented with your postgraduate student. Thank you very much all for attending. We want to also thank our host, the Ahmadu Bello University Zaria, for giving us this opportunity to do a presentation for them. We look forward to having other sessions with you in the near future. سبحانك اللهم وبحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك. Malam Yusuf, do you have anything to add before we close?
Oh no. Okay, thank you. I don't know whether Dr. Sahabi is there.
Yeah, I think Sahabi Ali Yusuf. Okay. Yeah, please. Yeah, we are looking for you to say a few words before we close.
Please, I think I don't have much to say except to deliver my sincere apology to the presenter because we are having so much issue in driving that there is a shutdown of the telecom services and the power is completely down almost 24 hours. So I keep on trying to communicate with the connector, and I want to salute the preparedness for being able to still proceed even after my request that can give. I don't want to miss this presentation, so I keep on suggesting things can't just postpone until another thing. But you told me, why don't you just push on that then because there are other people that also want to see the wisdom of the tenderness of what people are saying. Leave yourself my sincere apology and that this kind of presentation. So let me start for all of us. Thank you very much for a wonderful presentation. I think I joined it maybe 30 or 10 minutes ago. Still doing what? Questions asked. Thank you very much.
Thank you very much, Malan Sahabi. The voice was not clear, but from what I could grab, Malan Sahabi apologized for their inability to join the meeting due to power and telecommunication issues that they have. And they are very grateful for the presentation, and they look forward to having other sessions with us in the near future. All right, we call it a day here. Thank you all for attending, and see you in our next outing. We have these sessions once every month, mostly on the last Thursday of the month. And our next session is going to be on research methods in computing. So we look forward to all of you joining us and to benefit from some of the experts that we will invite in our next meeting. Thank you very much, and see you soon.
Okay, thank you guys.